Okay. Hello, everyone. Welcome to today's webinar. I'm Antriksh, and I'll be the host for today's webinar. I'm glad to welcome Dr. Shahin, who will present optical side channel attacks through chip backside, threats, challenges, and opportunities. Before he starts his presentation and today's webinar, I would like to share some news on hardwear.io that's coming up in the month of July. We have 4 days of trainings and 2 days of conference lined up for you from the 5th to the 10th of July. If you have some cool research, our CFP is open, so please send in some papers. We have also carefully selected 7 amazing trainings which are hands-on and some of the best in the industry to guide you and share their knowledge with you guys. Our presenter today is Dr. Shahin, who is an assistant professor at Worcester Polytechnic Institute. His research interest includes physical security evaluation of embedded systems using ICs, failure analysis techniques. Today's webinar will cover optical side channel attacks conducted from IC backside. He will focus on the reasons behind the lack of backside protection, and we will also assess some real world scenarios during the presentation. I was told, and I'm told by Shahin, that it's going to be more of workshop style. So yeah, lots to learn from you, Shahin. Some housekeeping rules for the audience. If you have any questions, please send them across via the Zoom chat. I will moderate them and we will take the questions after Dr. Shahin finishes his presentation. This webinar is also recorded and we will upload it on our YouTube channel for your future reference or views. Now I would like to invite Shahin to begin your presentation.
Yeah, thank you. Thank you very much for the kind introduction. And I would like to also to welcome everyone to my talk, which is about optical side channel attacks. So as it was mentioned, today we are going to talk a little bit about different optical side channel techniques. And so the format of this presentation is more like a tutorial. But let me first start with the hardware root of trust, which is a component basically available in many of our products, in many digital embedded systems, from our personal devices, from the electronic systems in our infrastructure, and also these systems and these electronic embedded systems are communicating continuously with some cloud environments, to transfer data, of course, over a telecommunication backbone. And of course, in all devices, or all embedded devices which are involved in this environment, we have usually a piece of hardware, which is called root of trust, which is responsible for storing different assets like secret keys, like biometric information, or other important information. And these assets are usually used to assure confidentiality of the process data, and also to assure the integrity of the communication that we have in this huge network. But as you all know, in this community, pushing everything to the hardware doesn't make necessarily everything secure. We know for more than probably 2 decades now that so computation on a chip is a physical phenomena, which means that when you are doing some computation on a secret or on some assets, the information leaks through some unintended side channels. Examples are, like power consumption, temperature, timing, electromagnetic radiation from the chip. And so these are probably the most popular side channel techniques that, researchers are investigating. But on the other, end of a spectrum, we have more sophisticated attacks, which are more destructive, but much more powerful, like microprobing. If you have access to some failure analysis equipment, you can open the package of the chip, and then you can put your needles on some metals or on some transistors on the chip to probe some information or eavesdrop some information on the chip. So in the middle, we have another class of attacks, which I refer to them as optical attacks, which are not so expensive as, like micro probing attacks, but they are much more powerful than classical side channel analysis attacks. So what are these techniques, or what are these optical techniques? When I'm talking about optical attacks, I'm referring to techniques which are usually rely on known IC failure analysis techniques. So in IC failure analysis, failure analysis engineers, they would like to debug or find the defect, after manufacturing, when an IC is fabricated. So a failure analysis engineer comes and try to probe, or interact somehow with transistors to understand how they are behaving, and probably find the defect. So the same techniques can be misused to attack, a chip. So we have techniques like photon emission, laser stimulation, and optical probing. So in this image that you see on the right, the photon emission is a passive technique in terms of it's similar to a power side channel. Basically, you don't really interact with the chip. You don't stimulate anything, but you have a camera usually, and then from the backside of the chip that you have only silicon, you can put your camera on and try to observe the photons which are emitted from CMOS, from the switching CMOS logic. And basically, these photons carry usually some useful information. At least they can show you what, for example, where an IP core is located, then it becomes active. We have more active techniques like laser stimulation or optical probing, where you are more active. So you have a laser source or a light source, you illuminate the chip from the backside, from the IC backside. For example, you park your laser on a single transistor. So you have two options. Either you stimulate the transistor and looking at the power changes or power consumption changes or current changes on the power line to get some information, or you directly look back at the reflection of the light, which gets modulated based on the activity of the transistor, which is probably the most advanced optical technique, which is called optical probing. So I'm going to talk about all of these techniques in details. And why, let me first mention why we are interested from the backside of the IC, to attack from the backside. The reason is that on the front side of the IC, we have different layers of metals. And so these metal layers actually obstruct the optical paths from transistors to the microscope. But on the backside of the chip, there is only silicon. And silicon, from physics, we know that it is transparent to near infrared spectrum. If you use or you do your analysis in this near infrared spectrum, nothing is really on the backside of the IC to obstruct the photons, which are traveling in both directions. So therefore, it's much easier to analyze the chip from the backside because you don't have any obstruction. So in the older days, probably when I started my PhD in 2013, still we had these old packages, which are still, many microcontrollers are built with these kind of packages, like QFE packages. And to get access to the IC backside, we had, polishing machine that, we were doing this kind of polishing on the backside of the chip to remove the plastic package and, get access to the silicon. So, and, afterward, we had to design our own custom PCB to solder these kind of chips upside down to start the analysis. And usually the setup looks like this, that you have a microscope, which is usually part of a IC, is a part of a setup from failure analysis equipment. And then you can take a look, in the near infrared spectrum, you can take image from the chip backside, and then you can zoom, you can find, localize your point of interest, etc. And this is an example of an Intel, or formerly Altera, Cyclone 4 FPGA manufactured with 16 nanometer. So you see a lot of regular structures everywhere, which are related to the logic elements or the resources that can be programmed by the user. Now let's talk about a little bit about the photon emission analysis. I said, if you remember, we have a camera, we can, and usually it's a CCD camera or InGaAs camera, which is sensitive to near infrared photons. and then we can turn it on and do a special photon emission analysis. In this example, you see we use an Intel Altera Max 5 CPLD, and in this figure you see actually 3 different logic elements. So each logic element contains a lookup table, plus it's similar to an FPGA. You have a lookup table, and then you have a dedicated flip-flop. So in the first image on the left, you see that we activated the lookup table. We programmed the lookup table with an XOR gate, and then we just gave inputs 1 and 0 with 2 megahertz frequency. And you see that all transistors which are involved in switching, they are emitting photons. Each spot in this figure is actually representing a single transistor. But what happens if so this is the combinatorial logic. What happens if you implement something sequential, which needs a flip-flop? This is what you see here. And you see 2 bright spots. The brightest spots actually on the figure, they are actually the clock buffers, which help a reverse engineer to localize where the register or where a flip-flop is actually located. And the reason that the spots are the brightest ones, because the rate of photon emission is proportional to the switching frequency, and clock frequency is probably the highest in most scenarios, is the highest frequency on the chip. And in this way, you can actually localize sequential logic in comparison to combinatorial logic. And you can see that, for example, in this logic element, not so much combinational activity is going on, but still the clock is active. So at each clock cycle, the register is getting fed with the clock. Another example, this is a counter, bit 0 to bit 4 of a counter, which at each clock cycle, it counts up. You can see that, because the first bit of the counter is changing its state, at each count, you get the most emission from that. And when you go to higher bits, to the MSP bits, you see that the emission becomes less and less because the switching activity is actually becoming less. Still, you can recognize the clock buffer in all of these logic elements. So these are some examples, to show you that in early days, how photon emission could help us to localize some points of interest or some functionality which was, we were looking for, and then we wanted to attack later on these things. So these are examples of also spatial photon emission, but we can also do combine spatial photon emission analysis with temporal photon emission analysis, which means basically you can start seeing how the signal is getting propagated over the chip. So this is again, this is an inverted chain with 10 inverters, and it is implemented on a Max 5 CPLD. And you see by having a temporal photon emission capability, you can basically create a video, which is called picosecond imaging circuit analysis. You can follow how the signal is actually getting propagated over the chip. And again, each spot that you see in this video is a single transistor, either PMOS or NMOS, which are showing up. And each frame of this video is 10 picoseconds. And this was actually presented at CHES 2014, where we wanted to show people that we can actually characterize an arbiter path, the delay of an arbiter path, and you can break the arbiter path in a linear way. So I leave the video to go, and you can also see on top, that the signal were coming in and the output buffers that the signal going out. So it contains a lot of information, of course. But after those early days, whenever we had some presentations in some conferences, so everybody was telling us, it's a very nice academic work, but in a real world, probably the chip preparation is a little bit challenging, and you need to have your custom PCB. Localization and reverse engineering are time consuming, especially on most recent chips with millions of billions of transistors and gates. Probably smaller technologies are not susceptible to optical attacks. And in general, having this equipment that you have to conduct this kind of attacks is probably very expensive, which makes these attacks non-realistic. So in this talk, I'm going to give you some real-world examples to debunk these misbeliefs or these myths. And for that, I'm going to present first 2 case studies, which is about what we have done to attack the FPGA Bitstream encryption. So for those who are not familiar with FPGA Bitstream encryption schemes, I introduce it very briefly. So in the case of FPGAs, most FPGAs are based on, they are SRAM based. So they don't have any non-volatile memory to keep the user configuration. Therefore, you need to store the configuration outside of the chip in an external NVM. But there is only one memory or 2 memories, actually, non-volatile memories on FPGAs, which are used for storing a secret key, which are battery BBRAMs or eFuses. So a user or a designer actually store a secret key in an FPGA in a trusted field, and she actually going to encrypt the design with the same encrypt key. It's the same symmetric key or red key that she had, store it on an NVM, and then later in the field, the encrypted bitstream gets loaded to the FPGA from the NVM, and there is a dedicated AES decryption engine on the FPGA which decrypts the bitstream. Now we would like to see, is it possible in a real scenario to either localize where the bitstream comes out, the plaintext bitstream, which contains IP information and other assets, or localizing the key inside the battery BBRAM, for example. For that, I'm going to introduce more advanced techniques. I mentioned in the second slide, optical probing. I talk about it here a little bit more. So in the optical probing, basically, as I said, you have a light source. You illuminate with your laser the backside of the chip or one of the transistors. And then we know from semiconductor physics that part of the light is getting absorbed in the silicon, and part of photons are getting reflected back. And we know again that changing the electric field, which means in this case the voltage or the state of a register, for example, or a gate, actually changes the absorption coefficient and the refractive index. Which means if you hold your laser here and you take a look at the reflection, your reflection is going up and down based on the data which is passing through that transistor. This technique is called EOP, electro-optical probing or laser voltage probing. So, but we have also more advanced techniques. If your laser scan an area on the chip, you can basically look at the detector for a specific frequency, and then you localize all gates or all nodes which are switching with that specific frequency, like, for example, a clock frequency. So this is called EOFM or electro-optical frequency mapping. Also in the failure analysis, it is called laser voltage imaging. So both are basically the same technique. And now take a look at the packaging and the challenges that were believed to be preventing researchers to do these kind of attacks. So I showed you that in earlier days we had this kind of QFE packages. You had to really depackage them. But the more recent chips, especially FPGAs and processors, they are all available in flip chip packages, which means the chip, the die, is already upside down, located inside the package. And what you see in this image, for example, this is a Xilinx Kintex 7 FPGA manufactured with the 28 nanometer technology. What you see in this image is actually the silicon itself. So you don't need to do anything. If you put this chip under the microscope, near infrared microscope, there you go. You can see the entire die from the backside of the chip. You can see also these engravings that has the model, the part number, and also the country that it is manufactured. And now if you have the image of the entire die. Now the question is where I should look for to find the important information. If you take a look, you see a lot of regular structure, but in the middle you have some irregularities also on the bottom. So let's zoom in the middle, because there should be, at that place where the irregularity exists, there should be some ASIC, which is related to configuration logic and also probably the decryption engine on the FPGA. There you see, this is, we found that we see probably 3 different structures here, but still we don't know where we should look for. Now the optical probing comes into play. So, or the first technique, EOFM, electro-optical frequency mapping. We just, did some analysis. We configured the FPGA in a loop with an unencrypted bit stream. And we did EOFM, and we looked for the clock frequency. We looked for gates which were switching with the clock frequency. Only the right side of this device becomes active. But when you do, when you configure the FPGA with an encrypted bit stream, so the bit stream, that it should get decrypted. Suddenly, the left core is also becoming active. So now you can conclude that the left part is related to the kind of AES engine, which is responsible for decryption of the FPGA, and probably the right core, we call it just the main core. And then, the laser scans, and we can really see individual gates with our desired frequency. So if we want to find now in this huge area where the bus is located, so the bus which is connected to the output of the AES, which carries the plaintext information, we can play with the bit stream. We can put fake bit stream data with repetitive patterns into the bit stream to create our own desired frequency. And if you do that, basically you can find out that we found out that there is a 32-bit bus which is connected to the AES engine. And we also realized that the same points of information or probing, probe point is also this information going back to the main core. And then from there, the entire configuration is getting distributed all over the FPGA. And if you go, for example, with your laser, park your laser on one of these bus buffers or bus drivers, then you can probe ones and zeros. Basically, this is like bit 0 or bit 2, an example I give here. You have period of time that your AES decryption engine is busy, and then it just sends out the plaintext information. And then if you wait on the corresponding bit addresses, you can probe the ones and zeros. And again, after that part of bit stream that got decrypted, again, the AES becomes busy for the next partition of the bit stream to decrypt that. So that was an example how to localize this kind of bus and probe the plaintext information. But also now we are more looking to the key itself. So it's more interesting probably to find the key itself, because then it becomes much easier to decrypt the bit stream than offline if you have the key directly. So we have a technique also I mentioned in the second slide. It is called laser stimulation. So in the laser stimulation, in contrast to optical probing, the laser scans, but in contrast to optical probing, we are not looking at the reflection of the light, but we are looking at the changes in the power consumption or in the current that is resulted from the beam of the laser. And again, from physics, we know that if the laser is passing through E-similar material, it creates some voltage source, which is called Seebeck voltage source. And this actually can help us to read SRAM cells. How? So basically, on an SRAM cell, I'm talking about the left figure, you have 2 transistors off and 2 transistors on. Then your laser hits or is passing through this similar material between drain and the channel. So it creates a voltage source which opens one of these off-state transistors for a short amount of time. So then you have a short circuit or transient short circuit for a very short amount of time, and then suddenly you are expecting a peak in your power consumption. And basically, by having the laser position and knowing the transistors, by scanning all 4 transistors, either you get a matrix like this, which is, and by the way, this matrix is not an image. This is just showing at which location you see a change or peak in your current consumption. Black means that you don't see anything. So, and if you use this on the battery backed RAM, this because that of Xilinx FPGAs, this is what you get. this is a battery background of a Xilinx ultra-scale FPGA, which is manufactured with 20 nanometer technology. And then you can see all 256 bits of the key, which is used for decryption of AES. Which is used by the AES to decrypt the encrypted bit stream. And then for fun, we just, programmed one of the bits to 1 and shifted 8 times. You can see that each of these legs are representing 1 bit, right? And you might say, why I see symmetric shapes? Because, 4 cells are combined together and, placed together, and they are mirrored. So, and then therefore you see these kind of symmetric shapes in this figure. And you want, of course, to extract the full 256 bits in an automatic way. So what you need to do, if you profile a training device or a training FPGA with a key, with a key which is all set to 0, and then you have your target or victim device, you do the TLS on that. It's basically a very easy image processing task. You can write a Python code to subtract these images, and then you can extract the 256 bits of the key from the entire RAM. And of course, in this case, we had a little bit knowledge of how SRAM cells are reacting to the laser stimulation. But even very recently, we showed, even if you don't know anything about the geometry of memory or registers, actually, deep learning can help you to extract the key without any reverse engineering effort. That's amazing, because usually we had all this knowledge how probably an SRAM cell has 4 transistors, the register has is different like this, etc. And if you go to some specific chip which doesn't follow the usual design patterns, then probably you cannot extract the information so easily. But if you have a device, you can profile it with deep learning algorithms, or like algorithms like CNNs, and then you can run these images, run these models on a victim chip, and without knowing anything about the layout and placement and routing, you can extract the key. And so these were 2 different real world scenario attacks that I showed, basically on Xilinx FPGAs, how you can localize the plaintext bit stream, which comes out from the decryption engine, and how to localize and read out the key from the battery background of the FPGA. Now I'm going to more advanced and more recent optical attacks, which is called laser logic state imaging. So one problem that optical probing or photon emission they need, as I mentioned, you need to have repetition, because in case of especially optical probing, the examples that I showed you, you need repetition because you need to modulate the laser light, the laser beam, when it gets reflected back. If you want to modulate it with a specific frequency, you need to keep your registers in a loop. And of course, for those of you who are active in the area of side channel analysis, you know that there is a very strong and sound countermeasure, which is called masking. So basically, masking prevents you from doing repetition on the same data. How does it work? Basically, it uses the concept of Boolean masking. You share your key to different shares in a way that, for example, if you use Boolean masking, you can add them, you get your real key. And then based on the T-probing security model, it was shown that if you have not enough number of probes, you cannot, and if you cannot probe all shares, then you don't get the key. And of course, there is a randomization of shares. So at each clock cycle, you get the new shares because of some TRNG which is implemented. You get new shares, and those if you want to repeat now those experiments that I showed you with these kind of things, if you want to extract the secret key from an AES, for example, It's not possible because every time you get a different data, you don't really see anything when you are doing optical probing. So, and this is exactly that we discussed, like the laser is scanning in X and Y direction, and usually we need to feed each individual transistor with a repetitive pattern, like with 1 megahertz. Then we can realize where these transistors are located. But a more recent optical technique actually was introduced in the field of failure analysis, which we have also used it to attack these kind of masking schemes. So it doesn't really need that you repeat, or give a repetitive pattern, or keep your circuit in a loop to do this kind of analysis. Instead, if you can halt your chip, halt your clock, you can modulate the power line with your desired frequency, and that has to some extent the same effect. So basically, when your laser scans this area on the chip, when it hits the on transistors, which are modulated on the power line, you will be able to read out or create a snapshot of all registers and extract the entire, all values from all these flip-flops. And you can imagine this is so powerful. If you know the place of the key registers on the chip, you need only one single snapshot to extract all shares together, and then you can XOR them together. You get the key. We showed that even if you don't know the locations of the registers, which is most of the time the case for this kind of optical attacks, you can have multiple snapshots in consecutive clock cycles. And using SAT solvers, by knowing the architecture of the cipher which is used, and then it reveals again the key. And this result is going to be presented probably in 1 or 2 weeks at IEEE SMP. So you're welcome to attend this talk. But just give you one of the results that we have in the paper. So this is an LLSI on a single register on this FPGA, Intel FPGA. So you can see that, you can clearly see that if a register is 1 or 0. And if you apply it to a masking scheme like an AES with 5 shares. And so in this example, this is one of the scenarios where we know where the key registers are located. And you can basically at the same time probe all 5 shares and read out. So these are the first byte of the key, of course, to be precise. So you can probe all 5 shares at the same time. So now at the end, I would like to talk a little bit about the attack effort assessment. One of the critiques that always we get is resolution, because we are using infrared spectrum, and from physics we know that the resolution is limited by the wavelength. If you want to have a higher resolution, you should go to the shorter wavelengths, to visible light, or even beyond that, which is problematic because the silicon, it's not transparent to those wavelengths, and we have to stick usually to the infrared wavelengths. And people are saying that, okay, your laser spot is so large because you cannot make it smaller. Your resolution is probably 500 nanometer, or your laser spot is, the diameter of your laser spot is 1 micrometer, but you are trying to attack a chip with 20 nanometer or 16 nanometer technology. So this image clearly shows you, this is an image obtained from the Xilinx Kintex 7, which is manufactured with 28 nanometer technology. It shows that it doesn't really matter what is the technology of your chip. The main factor that enables us to probe the data is the distance between the probing points. You see that the the distance is in the factor of micrometer, 2.5 micrometer, or even in some ASIC part, 4.3 micrometer, which is very easy, for us to, even if our resolution is bad, as long as these points are far apart from each other, you can start probing this data. Even, I should mention that even if the neighbors, you have a bunch of transistors very close to each other, but they are all switching with the data together. Again, an adversary doesn't really care if she's probing one transistor or multiple transistors, as long as the probing information or the modulation of the light is data dependent, so the goal is actually achieved. And the time usually that you need to do these kind of attacks, probably the most time consuming experiment that we have done took only 10 days of lab time, like 10 days at each day, 8 hours. And for example, extracting the battery background of the FPGA, the entire experiment reverse engineering took only 7 hours. And you should keep in mind the reverse engineering part or the profiling phase only usually for a family of chip, it happens only once. You don't really need to, you don't need to repeat this for other victim chips. If other victim chips are from the same series or from the same family, if you reverse engineer one of them, then you go directly afterward to the critical location and probe your data. Equipment, of course, we had access to the equipment, but you don't have to necessarily have access. You can rent it. And renting is like a few $100s per hour, like about $250 or $300 per hour, including operator. Which means for our worst case scenario, which only took 10 days, the worst case total cost will be 20K to 30K, which is in many scenarios is very cheap. If you are looking for a specific IP information or reverse engineering a chip, so the IP itself costs much more than this this price. And finally, a little bit about the countermeasures. So this is the work of my colleagues, my former colleagues, let's say at TU Berlin. So they are developing a specific coating layers on the backside of the chip. And please keep in mind that if we have something like a passive coating or passive heatsink, that doesn't help because the adversary can remove that without any consequences, right? So we should have somehow some active layer or active coating on the backside of the chip, where when the adversary tries to remove part of that or damage the coating or this layer, then you should have a sensor to detect that. So the problem is that on the backside of the chip, you don't really have any active devices, so you can't really realize anything meaningful. But the same concept, the same principles from photonics, they are not only good for attacks, but you can also use them in a positive way or constructive way to create a sensor. Basically, if you have a light source, you can have a beam of lights on this coating layer, and then the reflection is getting detected by some, junctions or PN junctions in reverse bias. And if the adversary tries to remove the layer, this reflection behavior will change, and then you are able to detect that something has happened on the backside or the tampering has happened. You can even create a puff based on this kind of coating layer. But on the other hand, I would like also to say that this is a relatively new topic in hardware security. So optical probing is very new in comparison to other optical attacks like photon emission and thermal laser stimulation. All of these techniques are need more research. If you want to have countermeasures, you need to probably combine different sciences together. Traditionally information theory and cryptography, like masking schemes, that helps a little bit, but you saw that more advanced techniques still can break them. Maybe you should go to device electronics and material science to see how you can change the next generation of chips with more, with materials which are not so reacting to optical techniques. You need to understand probably your circuit design a little bit, add randomness, etc. Everything together to have a better countermeasures. An example which we have done recently with my former colleagues at University of Florida, using standard cells, putting dummy gates in a very in the neighbor of the real gate, that you can create noise by complementing switching activities, for example. Or you can have more detection-based sensors. What if you can have, and by the way, this kind of analysis that I showed you, They are usually done by laser beam, which has a longer wavelength that is usually used by laser fault injection. And so there is no photoelectric effect on the chip. So it means that if you have even a light sensor, it's not going to trigger if the laser hits. The laser only heats up, transistors on the chip or the silicon. So you need to have some circuitry which is sensitive to the temperature, a local temperature increases. I mean, in this example, we implemented some network of ring oscillators all over the chip, and we were monitoring the frequency of all these ring oscillators in comparison to each other. And then if one of them starts showing a different frequency, then we can understand that something is happening. But still, a lot of much more research is needed in this direction to find out and discover new countermeasures against these kind of side channel attacks. And I would like to conclude on my talk here. I would like to really emphasize that backside protection is necessary. Going to smaller technology sizes doesn't mean that your design is secure. And by the way, even if optical probing or the optical techniques in general doesn't work, still failure analysis engineers are looking and inventing new kind of failure analysis tools to debug those 5-nanometer chips, for example. So just by thinking that we are going to smaller technologies, it's not the right approach to think that your design becomes secure. I showed you that specific packages, especially flip chip packages, the attack is mounted in a non-invasive manner, which is similar to like EM attacks or power attacks. So in some cases your attack effort is very very low because you don't really need to prepare anything. Again, measurement equipment can be rented. And finally, we showed that optical interaction is not only good for attacks. You can probably use it in a constructive way to design countermeasures. And finally, I would like to acknowledge all these people because this presentation that I presented today was a collaboration with all these brilliant guys at different institutes in Germany and the US. And with that, I finish my talk. And yeah, thank you for your attention.
Thank you, Shahin. Friends, if you have any questions, please send them across via the chat. Shahin, there is one question that's come. I'm going to read it out for you. It's from Upper. What is usually the next step after finding vulnerability in a particular target chip? I believe the vulnerability is reported to the vendor. If yes, what is their response most of the time? Because manufacturers like NXP are already coming up with chips having side channel countermeasures.
Yeah. So this is the most tricky part. It depends. I mean, there is not. I mean, some companies or some vendors are more open to these results, and but some probably smaller companies, they are getting panicked. But always all these analysis that we have done, I showed some results on Xilinx FPGAs. We informed them 4 months before writing the paper, not publishing the paper, even writing the paper. We showed them the results, and they agreed that we can publish the paper, for example. But the same thing like in other venue that you see all of these cache side channel attacks on, for example, Intel chips or AMD chips. They are all also getting communicated, to have responsible disclosure. And keep in mind that we are not breaking chips because it's just because we want to have fun or we want to have papers. We are trying to explore vulnerabilities, to warn the community about these threats, and based on that, we hope that more effort is getting done to create countermeasures. Like this optical probing that I mentioned, this is now probably got a lot of attention, especially from DARPA. So hopefully in future we see more programs on designing countermeasures for these attacks.
Okay. Another question from Sachin. He thanks you for the presentation. And can you elaborate on the repetition comment? Is this temporal repetition or repetition with different vectors?
So let me go back. I don't know the comment regarding the vector. What does that mean? But usually what I mean is that if you want to measure, for example, on the left figure, you have 3 transistors and you want to see their content. So when the laser scans, when the laser comes to this transistor, it stays there for a few milliseconds. And in that period, I need to create a modulation on the laser light. And for that, the simplest thing is that I give the same data to the flip-flop, reset, give it 1 again, reset, or give it or feeding it the clock signal or something like that in a repetitive pattern to this flip-flop, that when the laser stays there for that few milliseconds, I get some modulation and I can detect the location or the content of the flip-flop. But again, as I mentioned, in more advanced techniques, you don't really need to have the repetition of the data. You can halt the clock or freeze the clock, and then instead you modulate the power line. So the modulation of the power line changes the electric field on the transistor. It creates the same effect as the repetition, more or less. And then when your laser stays at each of these points for a few milliseconds, you get enough variations or up and downs that you can understand that this register has a 1 or 0.
Okay. Any other questions from the audience? Well, Shahin, I think that was it. Thank you so much. Amazing presentation. I'm sure our audience got to learn a lot from you. And thank you for sharing your knowledge as well with us. Friends, if y'all would like to submit your research paper to us, our conference is coming up in July. Our call for paper is open. We would also highly appreciate if you give a shout out to Shahin on your social media with regards to this webinar of his. Please send us your feedback, what you liked, what you don't like, so we could improve next time. Thank you, everybody, and stay safe until the next time.
Thank you.
Thank you, Shahin.